gracias y buenos días. Primero, lo siento. Mi español es bueno, pero mi habla inglés. So in this session, I'm going to talk to you about the use of organic acids and phytogenics to promote intestinal health. The talk is going to really be split into two parts. So I'm going to talk initially about organic acids, and then I'm going to move on to talk about phytogenics. Now, for some people, the use of organic acids in animal husbandry or farming is new to them. But for many years, man has been using organic acids or microbes for food preservation purposes. So on the screen here we have examples such as we have examples on the left-hand side, yogurt. In the middle we have pickling, and we also have cheese making. These are examples whereby you can inoculate food products and use their fermentation to preserve the feed. So we can also use organic acids directly in a pickling process to preserve foodstuffs. If we didn't do this process, the shelf life of these products would be very short. And there's evidence of cheese making dating back to 6000 BC. So for a long time, mankind has been using microbes and their fermentation products to preserve feed. A lot of the information and understanding of how food spoilage was occurring is thanks to the work of Louis Pasteur, who understood that food spoilage was caused by microbes. And that was the first point in time we understood this process and then understood how to properly preserve feedstuffs. If we just touch on some of the key organic acids, the ones up on the screen here are the monocarboxylic acids, a selection of those. And you can see that if we look at the formula, as we move down the list, the molecular size is increasing. We also see that as the molecular size increases, that at room temperature, the form of these organic acids moves from a liquid to a solid. We can also see the pKa value, which is relevant in terms of how much of the acid is dissociated at a particular pH. So the pKa value tells us the pH at which half the acid is dissociated. And that will be important, and I will return to that later. We can also see in the final column that water solubility, and we can see that as you move down the table, as the molecular size increases, as they move from being liquid to a solid, so the water solubility decreases. All these characteristics of the different organic acids are very important in terms of how they are going to be effective in any medium, and that includes the intestine. So you can understand that if you have poor water solubility, that acid may not be so effective in the aqueous phase of the intestine. Another thing we need to consider with organic acids is that they are effective antimicrobials, but they're also differential. So you can see here that the values, minimum inhibitory concentration values for formic acid for E. coli and 2 lactobacillus species. The units here are grams per litre, and you can see that E. coli, we need a concentration, this particular strain of E. coli, you need a concentration of 2.2 grams per litre to inhibit the growth of E. coli. If you look at the 2 species of lactobacilli, you can see that the concentration required to inhibit their growth is over 10 times that for E. coli. What this means is at any given concentration, the formic acid is having a greater effect on E. coli than it is on lactobacilli. And it's this difference that is key to the way in which we can use organic acids to improve intestinal health. We can selectively promote some bacteria and suppress others. This is a diagram showing effectively the way in which organic acids are believed to work. I spoke previously about the value of the pKa value. The pKa value defines the pH at which 50% of the acid is in the dissociated state. The microbial cell is pretty impermeable to charged particles. So we can see on the slide there that if you have an H+ ion outside the microbial cell, the cell is pretty good at preventing that from penetrating the cell. What we believe with organic acids is that in the undissociated state, the organic acid is able to move into the cell. Typically, in an environment such as the intestine, the pH outside of the cell will be lower than the pH inside the cell. Most microbial cells are trying to achieve a pH close to neutral. Most parts of the intestine will be below neutral or heading towards neutral. This means that once the organic acid gets into the cell, it dissociates at a higher pH. We then get the ions, the H+ ion, the cation, and the anion, affecting cellular pH, but they also, in the case of the anion, is believed to have direct effects on things like protein synthesis or cause problems in terms of protein. The presence of the H+ ion and the anion in the cytoplasm of the cell, the microbial cell will try to prevent any shifts in pH. So what it will try to do is pump the ions out of the cell. This is an energy cost to the microbial cell. Also, if you have the presence of ions within the cell, you're also putting the cell under osmotic stress. And we know that, as I said previously, that the ions can also have effects in terms of denaturing proteins. If you put all of these factors together, what we see is that over the course of time, microbial growth is slowed and eventually the microbial cell will die. Now, in terms of the use of organic acids, and I put phytogenics because I'm going to go on to talk about them, but we're seeing a growing interest in the use of organic acids. The use of organic acids in animal production or in terms of poultry really dates back to the 1960s when there was work done to show that organic acids were effective against controlling salmonella. Since then, people have gone on to use them to try and control microbes in the feed, but what we're now seeing with organic acids is that we can have effects in the intestine. There are three key factors in terms of why there's a growing interest in organic acids. One is that we'll all be aware of, globally there is a decreasing acceptance of growth promotional use of antibiotics, and also all use of antibiotics. If you take, for example, the part of the world that I'm from Europe, we've had a ban in place on the use of growth promotional antibiotics for close to 10 years now. Other parts of the world, if you look, for example, in the US, they're now implementing similar practices and policies there. This is increasing the need to find alternatives, such as organic acids and phytogenics, which I'll talk about today. The other one relating back to salmonella is, in certain parts of the world and in all parts of the world, there is or should be an interest in decreasing enteropathogens from food animals. So if we know that organic acids are effective against things like salmonella, if we can control the salmonella in the feed or in the animal, we reduce the possibility of that transference of salmonella to the human. Another issue that we're seeing, particularly in Europe, is issues over the use of formaldehyde, which is used as a biocide to control things like salmonella. In Europe, we're currently in a situation whereby it's unknown if the continued use of formaldehyde in such a way will be allowed, and or if there will be particularly stringent policies in place in terms of the use of formaldehyde use for microbial control of feed. So those three factors mean that at this point in time, there is a lot of interest, and it's pretty critical in terms of, and I've seen a few presentations, in terms of trying to achieve current levels of production and also projected levels of production, these issues are things that we're going to have to try and overcome. I'm going to talk now, having covered off a bit of the background to organic acids, is their use in vivo. I'm just going to run through now some examples of data just to try and highlight some of the effects you will see. At the top of the slide there is kind of like an outline of the trial design. So in this trial there were 875 Ross 308 one-day oak broilers. The trial was run over 35 days. It's going to be quite a busy slide because there's a lot of data on it, but effectively we had 7 treatments with 5 replicates of 25 birds. All birds were challenged with an oral dose, 10 to the 8 colony forming units of E. coli K88. It was an E. coli K88 strain that had been used previously in challenge models, so we knew that the particular strain, and at 10 to the 8, it would cause subclinical challenge. We were not trying to induce clinical challenge. The mortality data confirmed that we achieved the goal of subclinical challenge because there was no difference in mortality across groups. At the bottom of the slide is the 7 treatments. I'll just bring the slide up to make it easier to see. Effectively, we had a control. We had 3 organic acid products at 2 different inclusions for each organic acid product. And what you can see here is using PCR, I assume everyone knows, but polymerase chain reaction, we were able to demonstrate that at day 35 in the seeker, we were at all the organic acid products at all the concentrations were able to reduce cecal E. coli. Most of them in the order of 1.5 to 2 log reduction in E. coli. If we look now at lactobacilli, again using PCR with primers directed against lactobacilli, we can see that in all cases, the organic acid products improved cecal lactobacilli, except for organic acid product 1 at the inclusion of 0.4%. This was intermediate to the control and the other groups. What this effectively demonstrates is the ability to use organic acids or organic acid products and affect the distal gastrointestinal tract in terms of microbial numbers. We're able to shift the E. coli down in this challenge, and we're able to promote lactobacilli. There won't be too many production sites, broiler production sites or other ones, that do not experience some degree of subclinical E. coli challenge at particular times during the production cycle, and so the ability of organic acids to be effective against E. coli and promote lactobacilli is very beneficial. If we look now at another parameter that is often used when we talk about intestinal health, and that's intestinal morphology. Again, this slide might be a bit hard to follow, but I will try my best. Effectively, this is 2 published papers from 2007. The top one, they used formic acid at either 5 or 10 kilograms per ton. There was no statistical difference in these parameters between 5 and 10 kilograms per ton, so the data represents the mean of those 2 treatment groups. What you can see is that with villus height, expressed as a percentage increase versus the control or the antibiotic growth promoter group, you can see that we get approximately a 16% increase in villus height versus control, and we get around about a 12% increase in villus height versus the antibiotic growth promoter. We can see also that if you then look at villus surface area, we get close to a 30% increase in villus surface area versus the control with the formic acid products. And we also see around about a 10% increase in villus surface area versus the antibiotic treatment group, growth promoter treatment group. If we look at the bottom part of the table, where this was a formic and propionic acid-based product in combination at 3 kilograms per ton of feed, in this situation there was only a control, and we can see that there was approximately a 15% increase in villus height versus a control. it can often be sometimes hard to show how these parameters, improvements in these parameters, may not always translate to improvements in performance, but if we look at the performance, we can see the average daily gain was increased by around about 12% versus control, and we saw an improvement of around about 6% in FCR versus the control. So clear demonstration that with the organic acid products, they were able to improve intestinal morphology, and there was a direct improvement in the performance of the animals. Some of the other parameters that organic acids are able to promote or improve are things like nutrient digestibility. So again, we have a study here. There was a background subclinical E. coli challenge. We can see that day 21, which is a traditional kind of like time period in terms of making nutrient assessment, digestibility assessments in broilers, we can see that there was close to a 7% improvement in crude protein digestibility. If we then look at tibia ash, we can see that at day 35, the broilers that were on the organic acid treatment had a 3% improvement in tibia ash content. So we know in any phytase type study, phosphorus availability or indicator of mineral availability is routinely tibia ash, and we can see here that the organic acid product is able to improve the mineralization of the bone. And again, when we talk technically, what we have to be able to do, particularly with our sales colleagues, is try and explain to them how all these parameters translate to improvements in performance, things that people can actually see and benefit from on farm. You can see the slide looks a bit familiar because this returns to the challenge model trial that I spoke about, where we saw those reductions in cecal E. coli, we saw the significant improvements in cecal lactobacilli, and it translated to improvements in performance. We can see here to varying extents, but all of the organic acid products at the 2 inclusions increase the daily gain of the birds over the 35 days. If we look at FCR, we see a similar effect. We can see that versus control, again, all of the products at all of their inclusions improved feed conversion ratio. Just as out of interest in terms of pulling this data together, I thought it'd be interesting to see how the relationship between gut health, here measured in terms of cecal E. coli and lactobacilli, how that correlated or related to performance. What you can see here, and I apologize because the X and Y axes are the wrong way around. Really, the micro parameter should be your predictor, but here it didn't look quite right when I had the graphs that way. But what you can see here is that as E. coli decreases, we see a linear improvement in daily gain. You might not be surprised by that. And we see the reverse in terms of a linear relationship between cecal lactobacilli and an increase in daily gain. You might think that's not too exciting, but what I find interesting was that if you then plot FCR, and I've expressed the linear part, we see a curvilinear relationship between cecal E. coli and FCR. And you might think, well, what's so interesting about that? But if you then plot the data again for cecal lactobacilli versus FCR, we again see a curvilinear relationship. Now, the next thing I need to do, these are correlating the treatment means, and what I'll do next is correlate the replicates. But what in essence it indicates is that there is a difference in terms of the performance you might see if you change cecal E. coli in terms of, it looks like the linear relationship means that as you decrease E. coli and increase lactobacilli, you see a straight line relationship in terms of performance, but it's a curvilinear relationship when you look at FCR, meaning that the lowest level of either may not be optimum for FCR. What I think this suggests is the potential to use organic acids to effectively, depending upon what parameters you're looking for, and most people obviously want improvements in daily gain and FCR, but there is a potential to, it indicates there may be the potential to selectively use organic acids to either achieve a daily gain improvement or an FCR improvement. If we look now at organic acids improving growth performance and immune response of phosphorus deficient and sufficient broilers, again, this was using Ross 308s. We had 5 reps at 20 birds per treatment using corn soy diets. Available phosphorus was reduced by 0.1%, and organic acid was used at 2 kilograms per ton and or with a phytase at 500 FTUs per kilogram. If we look at the results, we can see that we effectively, assuming that the positive control was meeting the needs of the birds in terms of phosphorus, we can see that we get a significant reduction on the far right hand side when you put the organic acid and the phytase together. So what you can also see in the middle, that the organic acid significantly improves FCR versus a negative control. So what this tells us is the organic acid on its own is able to improve the performance of broilers receiving a phosphorus deficient diet. It also means that if you're using a phytase and you use an organic acid in conjunction, you can expect to see additive effects in terms of performance. We also see a similar effect in terms of average daily gain. The other interesting thing, and what we're seeing a lot more of, is improvements in the immune response. And you can see again that the graphs effectively follow a similar pattern here. When you reduce or downspec the diet by 0.1% of available phosphorus, you can see that, as in all studies, you see a reduction in terms of primary IgG. What I mean there is that the IgG response is mirroring the performance response. You reduce available phosphorus, you reduce performance. And we can see here that we reduce the primary IgG response. If you look at the organic acid, that then restores the primary IgG response back to the positive control, as does a phytase. But again, if you add the two together, you see a significant improvement over the positive control in terms of the primary IgG response. We also see a similar effect in terms of the secondary antibody response or humoral response. So this tells me, I think this data is quite exciting because not only can we have effects in terms of performance, but it shows that using the organic acids alone or in combination with a phytase, we are able to improve the performance and the immune response of the bird. We know that organic acids do not really have a direct effect on viruses, but if we're able to improve the immune response, and this was to specific challenge, this was sheep red blood cells injected into the broilers and then measuring the response to that. What this tells us is that, for example, with vaccination, we may be able to expect an improvement in the response to vaccination using the organic acid and or with phytase. Most diets now contain a phytase, so we can see that there are additive effects in terms of using an organic acid alongside the phytase. I'll just check how I'm doing for time. So we also looked at some work where we were looking at the effects of an organic acid on broiler breeder fertility. And we can see at week 35, all of the birds here were artificially inseminated at 35 and 45 weeks. The organic acid was in there at 2 kilograms per ton, and we can see that there was approximately a 5% improvement in fertility. At 45 weeks, we saw approximately a 2% improvement in fertility. But for me, the most interesting information with this work was that we saw a significant, when the male broilers were selected from the parent breeder hens. They were then followed through to 42 days. They were not supplemented with any organic acid, and what you can see is that male broilers coming from organic acid supplemented breeder hens had a significant improvement in weight gain for both from week 35 hens and also week 45 hens. There was also, at week 35, there was no improvement in FCR, but we did see a 6-point improvement in FCR for broilers coming from supplemented hens at week 45. So we can see that we are able to use organic acids to improve the fertility of the breeder hen and also have a positive impact upon the performance of the progeny without directly supplementing them. I'm conscious that I'm running out of time, so I'm going to have to move a bit quicker. This is just effectively what I did here was pulled together some data where Dr. Gordon Rosen had done some meta-analysis for both antibiotic growth promoters and also acids. In the acid data set, it also includes both inorganic and organic acids. What you can see here is, at the very least, this meta-analysis revealed that acids were as effective as antibiotic growth promoters in terms of feed intake, live weight gain, and feed efficiency. So it tells us that there is a potential with acids to be as effective as antibiotic growth promoters. That's covered off the organic acids. Now I'm going to talk a little bit about phytogenics. Again, like with organic acids, when we think about it, mankind, animals have been using phytogenics, i.e. plant material, for health reasons for a very long time. There is some kind of stigma, or has been in the industry, in terms of the perception of using plant materials for in terms of animal production and also in terms of human medicine. But the reality is that medicine is already using powerful compounds that are derived from the natural world in terms of plants. On the screen there, you can probably recognize the poppy plant, which is where morphine was first isolated from, an opiate. We can also see on the right-hand side a Pacific yew tree, the bark of which contains a compound that is used in the treatment of cancer. And at the bottom there, I just have oregano, because that is what I'm going to move on to talk about specifically. So what are phytogenics? Well, the word phytogenic covers a very broad and diverse range of material and compounds. The word phytogenic just means from plant origin. We can subdivide these into herbs, botanicals, oleoresins, and essential oils. The difference between the bottom two is essentially the extraction process using either solvents or steam distillation. And in terms of this group of materials or compounds, it was estimated that there are somewhere between 250 and 500,000 different species of plants on Earth. So you can understand that this is a very diverse range of compounds and materials, and in the time I've got left, I can't possibly cover all of them. This is just a table showing some of the essential oils and their main components in terms of in animal production or in poultry production, some of the ones you might typically come across. We've got cinnamon, eucalyptus, ginger, oregano, rosemary, and thyme. I'm not going to go through the different compounds, but what you can see is that these are made up of different compounds at different percentages. There is some similarity, for example, between oregano and thyme in terms of the active or main components with carvacrol and thymol. But with all of these, depending upon where they're grown, how they're grown, etc., these values are only very broadly representative of the typical content, because if you analyze them, they will vary dramatically. That is the plant itself. We also know, as with organic acids, that phytogenics in vitro are very effective antimicrobials. We can see here we're in milligrams per litre. When we had the organic acids, it was grams per litre. And you can see that, and I'll use the E. coli, for example, 250 milligrams per litre to inhibit E. coli. Now, it won't be the same strain that was used in the formic acid slide, but what it does tell us is that effectively phytogenics are about 10 times as powerful as formic acid in terms of controlling E. coli. We can also see the second one up from the bottom, that it's also Phytogenics, in this case it's oregano, is effective against resistant organisms such as Staphylococcus aureus. And it's also effective here against yeast in Candida albicans. So we know that phytogenics have a broad range of antimicrobial activity and are very effective. In terms of the way that phytogenics work, we can see there's a degree of similarity with organic acids, but here we're using the EO stands for an essential oil. There's two main ways in which they work. They either penetrate the cell and interfere with things like mitochondrial lipids. Essential oils are able to break up the lipid and affect the production of ATP. Or they can affect the permeability of the cell membrane. So you get a loss of ions from the cell. The membrane is no longer able to do its job, and the movement of materials across that membrane is no longer regulated. This, again, similar with the organic acids, leads to depression of the ability of the cell to grow, and eventually the cell will die. I'm just going to talk now a few slides about the use of oregano oil. As I said, I can't cover off all phytogenic compounds, but I'm going to focus on those. One that's particularly familiar or used quite regularly in poultry production, so oregano oil. And here we're looking at a coccidiosis challenge trial, whereby this was run from 1 to 42 days, 5 reps of 10 birds. On day 22, all groups were challenged, other than the unchallenged control. 4 groups were challenged with 50 doses of liverpox T vaccine orally, containing 3 Eimeria species. The idea here was to induce mild coccidiosis. If we look at coccidiosis lesion scores, we can see that there was a coccidiostat used in the trial. The oregano oil was used at 300 and 500 grams per ton. And if we look at coccidiosis lesion score, 7 days after the birds have been challenged, we can see that the coccidiostat is intermediate to the 2 challenge group. No, apologies. We can see that the coccidiostat reduces the lesion score versus the challenged, and we can also see that the oregano oil at both concentrations also reduces coccidiosis lesion score 1 week after challenge. If we then look at daily gain during that period, we can see that the challenge group grew significantly slower than the unchallenged. No surprises there. We can see that the coccidiostat, the middle bar, was intermediate, but we can see that with the oregano oil at 300 and 500 grams per ton, we were able to maintain daily gain versus the unchallenged control. If we look at European efficiency factor as a kind of like a broader performance parameter over the course of the trial, we can see that both oregano oil treatments maintained the European efficiency factor versus the unchallenged control. And so we can see that we've had an effect on gut lesion scores, we've maintained daily gain, and in terms of over the course of the bird's life here to 42 days, we've maintained or kept the European efficiency factor at the same level as the unchallenged control. We also have data with non-specific coccidiosis challenge. So here, it was on a site where they knew there was coccidiosis challenge. They do oocyst counts on 10, 20, 30, and 40 days. Both an ionophore antibiotic and the oregano at 300 grams per ton reduced the counts on days 20 and 40. But in terms of performance, we saw weight gain maintained, but we saw that with the ionophore antibiotic and the oregano, that performance was maintained, but particularly with the oregano, at a lower feed intake. And of course, that meant that they were able to maintain body weight more efficiently. So we see a significant reduction in FCR for both the ionophore and the oregano oil. Again, a bit similar to the organic acids. Although this wasn't significant, the authors noted that the improvement in the increase in serum IgG, the numerical increase, was worthy of further consideration. So again, the potential of oregano oil to improve immune parameters is worth further investigation. I am running out of time and I need to speed up. But this is just some data. It's going to be hard to follow, but this is just looking at basically gene expression. They were looking at the expression of genes related to inflammation in the cecal tonsil, so lymphoid tissues associated with the cecum. I've ringed group E, which is the essential oil, and in all cases, whether it's numerical or significantly reduced, it shows that the oregano oil was able to reduce the expression of these inflammatory markers, which are known to be elevated with coccidiosis challenge. So the oregano oil is able to help reduce the inflammation in the intestine, or the indicators are that will happen. In terms of a summary, organic acids, effective antimicrobials, they help control microbes in the feed or intestine. That includes enteropathogens. Either directly or indirectly, they're able to improve nutrient digestibility and availability, gut morphology, immune responsiveness, improved performance, including of non-supplemented progeny. They're potent antimicrobial. For phytogenics, they're potent antimicrobials, including against viruses. They can mitigate key production diseases such as coccidiosis. They have immunomodulatory or anti-inflammatory benefits, as we've seen with the gene expression data that I had to run through quickly. And we see that this leads to better or more efficient performance. Just one more slide. The things that people need to consider in terms of using these products is the product form. Is it, for example, with an acid, is it a pure acid versus a triglyceride versus carrier protected? This will affect where the organic acid is having an effect. If you have a straight acid, it's very volatile, it could be lost or quickly metabolized in the intestine. Triglyceride requires a lipase to start breaking it down, so you won't see effects until you reach the intestine, the duodenum, where lipase is produced. You need to think about the components, which acids, which phytogenic compounds, which actives. All of these things will affect the efficacy that you see. In terms of phytogenics, is it a synthetic or natural compound? The big one, particularly with phytogenics, is product consistency. If you don't have a consistent product, you will not get a consistent effect. You need to think about how is the consistency achieved, what is the specification and ranges in terms of the oregano oil and its components, what is the inclusion, what inclusion do you need to be effective, what is the cost per ton of feed or per bird to treat. And the thing I've got at the bottom, my last point, is quite often when you talk to people, we're considering cost, but actually I think it's more relevant to think about return on investment, because if I was to give all of you, if all of you were to give me $1 and I was to give you $2 back, you would definitely do that deal with me. And there I'd like to leave it.